Okay, let's continue. There is one more concept in today's lecture. This is orthogonal vector. Okay. So, what is the orthogonal vectors? So, consider R2 or R3 and two lines through the origin determined by vector u and vector v. For example, if the space defined something like this, vector u and vector v is like this, right? Then in this case, these two lines geometrically perpendicular if and only if the distance between from u to v is same as the distance from the u to negative v. Okay, so as you can see here, if the length of the this one and this one is same, then we can say that these two lines or these two vectors are perpendicular. Okay, so then let's define the length of the u minus v, length of the u minus negative v. Okay, so first of all, distance u negative v here is going to be this one, right? From the definition of the distance and length, right? Then this one is equal to the square length u plus v, right? Square length u plus v. Then we can represent this one by inner product of the u plus v and u plus v, right? Then we can separate this one and this one with this one, right? So this and this one, right? So how can you do that? If you see the theorem 1 here, B, if you see this one, theorem B, we can easily decompose this one, right? Then what next? We want to decompose this one, right? So it will be this one. Okay, this one. Okay, let's write this. Theorem P, right? Then how can we do that? From theorem A and B, from theorem A and B, we can compute this one, right? Then what is this? The square length of u, right? So this, to summarize, the square u plus square v plus 2 times u dot v, right? So to summarize, the distance of the u and negative v is equal to square length of the u, square length of the v, 2 times u plus v, right? Similarly, we can define the distance u and v, this one, right? So from here, we can just modify negative v to v, right? So negative v to, or v to negative v, right? Because this is just the reverse definition, right? So this will be square of the length of v, square of the length of negative v, right? And 2 times u dot negative v, right? Then this is same, and from definition of the length, the length of negative v is equal to length of the v, right? Because the in the definition of the length, we didn't consider the sign of the vector, so it will be same, right? Then only difference here, negative 2 uv, right? So when you're comparing this one and this one, the only difference are here, right? But if you remember this figure, which tells us that the length of the u minus v is equal to length of the u minus negative v, right? So it means that these two terms should be same, right? So it means that 2u dot v is equal to negative u dot v. So which happens if and only if the u transpose v is equal to 0, right? It means that the inner product of u and v is equals to 0. Okay, so in other words, if inner product of the vector u and vector v is equal to 0, then we can say that these two vectors are perpendicular. Okay, so in other words, the corresponding line, just two vectors are perpendicular if and only if the vector inner product of the vector u and vector v is equal to 0. Okay, so what does it mean? Okay, let's say we have a two arbitrary vector in 2D space, something like this. Three arbitrary vector, something like this. Okay, let's say this is v u w. Then we want to know which vectors are perpendicular or not. So if we want to check this v u vector v and vector u perpendicular perpendicular, then we can check v1 that v that u is equal to 0 or not, right? What about this and this? We can check u w perpendicular, then we have to check transpose u is equal to 0. Okay, so by the way, so in other words, by using the definition of the inner product, we can check the some arbitrary vectors are perpendicular or not. Okay, so here's the definition. Two vectors u and v in Rn space are orthogonal to each other if inner product of vector u and v is equal to 0. Okay, so this is the definition of the orthogonality of the two vectors. Okay, so this is very important definition, which will be used in our Thursday lecture. Okay, so please keep in mind. And the 0 vector is also orthogonal to every vector in Rn space because 0 vector transpose v is only v, just v, right? So we can easily say that zero vector is orthogonal to every vector in Rn space, right? Okay. Okay, so from here, there's one more theorem. Actually, we already know the Pythagoras theorem, right? So in Korean, 피타고라스 정리. 네. 그래서 so if we go back to our lecture, so the vector u and v are orthogonal. Orthogonal means something like this. Vector u and vector v, right? Something like this. Then scalar length of u plus v. Scalar length of the u plus v. This is the u plus v is equal to scalar u plus scalar v here. Okay, scalar v, scalar here. Okay, so this is the Pythagorean theorem. So if we have the triangle, the length of these three lines have the relationship, something like this. Okay, so this is the Pythagorean theorem. Okay, so this is closely related to our definition of the length and the inner product, something like this. Okay. Okay, so here's the last one. So if the vector u and v are non-zero vector in either R2 or R3 space, let's just think about R2 space because this R2 space is easier to understand. Then there is a nice connection between their inner product and angle. So let's see this example. Okay, let's think about the 2D space, something like this. Let's say there we have the two arbitrary vector. This is the vector u, which consists of the two entries u1 and u2, and vector v with the v1 and v2, right? So this is the vector u, right? This is the vector v, right? Then the inner product between this u and this v is equal to length of u and length of v and cosine of the theta here. Okay, so it means that the inner product u and v is equal to this length of the u, length of v, length of cosine theta, right? So okay, let's prove this property first. How can we prove this? We can just use the law of cosine, right? So I think you know the law of the cosine, right? So what was that? So this is the u minus v, right? This is the u minus v. Then what is the length of the u minus v? It should be something like the square u and square v with minus 2 u times v times cosine theta, right? So please check this one. Maybe you learn this one in your high school. Okay, so please find out what was that. Anyway, so this is the law of the cosine, then which can be rearranged to produce this one, right? So if we can move this one to here, right? Then it will be 1/2 with the scale length of u, scale length of v, minus scale length of u minus v, right? Then what is this? this one, right? And what about this? It will be something like this. Then this one is something like this, right? Why? Because the u minus v is a new vector defined as u minus u1 v1 u2 v2, right? So this is the length of this one. Okay. Then if you remove some repeated values, something like this, from u1 plus u1 square plus v1 square plus minus 2 u1 v1, something like this, then we can remove this one and this one and this one, and from this one, something like this. Anyway, finally you can get the u1 times v1 plus u2 times v2, then which is defined as the inner product between matrix vector u and v. Okay, so in other words, inner product vector u and v is going to be length of the u times length of v times cosine theta. This one. So this is the another definition of the inner product. Okay, if you go back to the definition of the inner product, it was something like this. But if you know the length of the vector u and vector v, you can just compute the inner product between them using the theta between two vectors, right? So why this property is useful? Okay, so if you remember the unit vector, where was that? Here unit vector, if you remember the unit vector, length of the unit vector is 1, right? So case of unit vector, if the u and v are unit vector, then vector u dot v is equal to cosine theta. So what does it mean? In the 2D space or 3D or 4D space, let's say we have a matrix, arbitrary vector, let's say how can I read this? This, let's say W, let's say W, and K, like that. Okay, so let's say unit vector of the vector W is U and unit vector of the vector K is the V, right? Then actually we want to compute the relationship between vector vector W and vector K, but it's really hard to if they have the very large length difference, so it is hard to compute directly. So in this case, we can normalize these two vectors to the unit vector space, something like circle, right? Then the inner product between this one is only defined with the theta here, right? So what was the shape of the cosine theta? Cosine theta. Yeah, the shape of the cosine theta is something like this, right? So anyway, if there is the one unit vector u and one unit vector v and another unit vector, let's say a here, then by measuring the theta between them and this one, by measuring the theta between two vectors, then we can say that which vector distance of the vector u and vector v much similar than vector u and vector a. Okay, so it means that by using the this definition, we can just compare the two vectors by only using the by only using the angle between them. Okay, this is very nice property. So let me summarize this one in Korean. 이제 저희가 오늘 강의에서 계속 배웠던 얘기들이 이제 이너 프로덕트랑 이제 벡터 스페이스 상에서의 디스턴스, 그러니까 벡터들 간의 디스턴스를 어떻게 구하는지에 대해서 이제 배웠습니다. 그래서 이제 이게 왜 중요하냐면은 이제 우리가 어떤 스페이스 상에서 존재하는 어떤 스페이스 상에 존재하는 아비트러리한 벡터가 있을 때 이 벡터들 간의 시밀러리티를 보고 싶은 거예요. 뭐 시밀러리티라는 것은 얘들의 뭐 유사도일 수도 있고 아니면 얘들이 얼마나 떨어져 있는지 뭐 이런 다양한 어떤 지오메트릭한 릴레이션십을 보고 싶은데 이제 이게 나중에 뭐 다양한 어플리케이션에 쓰일 수 있는데 오늘은 뒤에서 이제 딥러닝에서 어떻게 쓰이는지 말씀해 드릴 텐데 그 릴레이션십을 보고 싶을 때 할 수 있는 여러 가지 방법 중에 하나가 간단하게 이제 디스턴스를 재는 거죠. 이 벡터 스페이스 간의 디스턴스를 잴 수가 있는 건데 사실 그게 가장 간단하죠. 그래서 뭐 이 벡터 W와 벡터 K의 랭스를 바로 재버리는 방법이 있을 거고 근데 이런 경우가 이 K라는 밸류가 이제 너무 많이 커져서 이 K의 랭스 자체가 U보다 훨씬 멀리 있거나 하면은 사실 K와 W 간의 어떤 스태티스티컬한 성질을 이 디스턴스로만 재기에는 이제 애매해지는 상황들이 발생을 해요. 근데 그런 경우에 사람들이 이제 많이 할 수 있는 게 뭐냐면은 사실 어떤 벡터라는 거는 이 랭스도 중요하지만 이 벡터, 이 W와 K 간의 이 앵글, 이 각도가 사실 얘네들이 얼마나 유사한지를 사실 나타낼 수 있는 지표가 될 수가 있거든요. 그러니까 무슨 얘기냐면은 얘네들이 비슷하게 가까이 있을수록 이 세타가 작아질 거고 얘네들이 성질이 완전 다른 벡터일수록 이 세타가 커지는 거죠. 그럼 이제 이거를 계산할 때 어떻게 하느냐? 사실 이너 프로덕트만 하면은 아까 봤을 때 이 랭스 벡터 U의 랭스와 벡터 V의 랭스가 계산이 돼야 돼요. 사실. 그렇기 때문에 사실 이 상태에서 이너 프로덕트를 하는 건 큰 의미는 없지만 이 이너 프로덕트를 하기 위해서 이 W와 K를 유닛 벡터 즉 U와 V로 프로젝션을 시켜서 그러니까 노멀라이즈를 시켜서 랭스가 1으로 만들면 어떤 하나의 서클 스페이스 서클에 존재를 하게 되겠죠. 그럼 그 유닛 벡터들 간의 이너 프로덕트는 그냥 코사인 세타만 남겠죠. 왜냐면 얘가 1이고 얘도 1이니까. 그렇죠? 그 말은 뭐냐면은 이때 이너 프로덕트는 이 코사인 세타로 표현이 되니까 이 이너 프로덕트를 계산을 해보면은 코사인 세타를 알 수가 있고 코사인 세타라니까 이 두 개의 벡터 사이에 우리가 각도를 알 수가 있는 거죠. 즉 그 각도라니까 이 두 개 벡터가 얼마나 유사한지를 저희가 하나의 지표로 쓸 수가 있는 겁니다. 네, 그 이제 저희가 이너 프로덕트랑 length of the vector를 오늘 배운 이유기도 합니다. 그래서 yeah, if we go back to the today's lecture, okay, let me give some more minutes. Let me give some one more minute. Where is that? Yeah, here. Okay, sorry about that. Okay, let's go back to our lecture. Actually, so this geometric concept, such as the inner product, the length of the vector, is one of the most important concept in the vector space. So those kinds of concepts will be used in our following lecture or our remaining lecture, something like the eigenvector decomposition or the singular value decomposition or the least square things. But uh, uh, this kind of concept will be used in the many kinds of the application, like the deep learning or the deep learning or the economic field or the statistic field, something like this. So please keep please remember those concepts, like the inner product and the length and distance of the vectors that we discussed today. Okay, so this is the same page. Sorry. So in other words, this proof can be extended to the R3 space. So this is used to define the angle between the two vectors, right? As I mentioned here. Okay. Okay. I bring one very interesting slide here. So actually, this is just a supplementary material, so you don't need to remember this. But I want to show you how this inner product or the distance concept is used in the other field, like the deep learning stuff. Okay, so this is the examples of the image classification task. So what is the image classification task? Okay, if we have some image, something like this, as a human, we can easily understand this is cat, right? But as a machine or as a okay, how to say, as some kinds of computer, they just see this image as some value, something like this, right? Because each pixel has some values like this, so it is hard to extract the semantic meaning from this image. So something like this is cat or not. So this is the image classification problem. So to solve this problem, there were so many techniques, but nowadays there is the deep learning based method, something like this one. So this architecture looks really complicating, but as you can see here, this is the input image. We want to recognize the class of this one. In this case, car, right? So even though this part is really complicating, but the output here is something kind of the vector, some kind of vector. Let's say y, vector y. So thing like y1 through the y and something like that. So what I want to do is, if we have the ground truth value, let's say, okay, this is car. So please try to understand this is car. So we want to train this machine to understand this car. So to do this one, we have to teach the output of this machine y is equal to the real output, something like 1 0 0 0 0 0 0. So the goal of this image classification is to minimize the similarity between two vectors y and ground truth y star, real y. So it means that if we can draw some kind of the vector u, vector y and vector y star, then we want to know these two vectors similar or not. So So to train this network, we try to this vector to close as much as possible. So to make this output is to close to the y star, we have to use the distance concept, which was defined in today's lecture, but there is a more variant about this one. Anyway, the concept is really similar. So to train this network, we use the concept of the distance. So this is the one example or the one application of the distance between two vectors that we discussed today. So yeah, I want to just show you this one. Okay, so this is the end of today's lecture. In the next lecture, we will talk about the other properties of the distance of the vector vector u and vector v. Okay, thank you.